I bet you guys have been sitting there wondering all day if I'd forgotten about you, and I haven't. um, Today, the first day of NTI. You guys are used to me doing the videos, but I have my Algebra 2 classes that are not used to the videos, and a lot of them were panicking, and it was an interesting day today. So I am going to create this video. We started this set of notes in class on Friday, or maybe it was Thursday. I believe it doesn't matter. We started this set of notes already. We made it through the first 3 examples, and I'm going to pick up here with example 4, where we're talking about factoring a quadratic by completing the square. So it says to find the zeros. Now the way we do completing the square, we take our given function, it's x squared plus 5x plus 4, and since we're finding the zeros, we set the function equal to 0. Now for completing the square, we're going to subtract the constant from both sides, and so now we have x squared plus 5x equals negative 4. And this is a very simple one to factor without doing the completing the square, but it's useful to see how to use completing the square to get the correct solution. I'm going to take a little side trip here. We know that this is going to factor into x plus 1, x plus 4, which means our zeros are negative 1 and negative 4. So completing the square, if we get something different, then we've done something wrong. Excuse me. So to complete the square, we take the linear term, which is the coefficient on x. In this case, it's 5. And we take 1/2 of that term, so 5 over 2, and we square it. And what we end up with is x squared plus 5x plus 25 over 4. And that 25 over 4, whatever the squared term ends up being, since it's 25 over 4, we add that to the right hand side as well. And so now we have x squared plus 5x plus 25 over 4 is equal to 9 over 4. And to finish this out, what we want to do is factor the left hand side of the equation. Well, the factoring is really simple. We take the term that we squared, in this case 5/2, and that is our factored form. It's going to be x plus 5/2 quantity squared. If I expanded that out, it would generate this whole left hand side of the equation. So the factoring is simple, is equal to 9 over 4. And then here we use the technique that we ended the class on Friday by doing the square root method. So if I take the square root of both sides of this equation, I get x plus 5/2 is equal to plus or minus 3 over 2. Square root of 9 over 4, both of them are perfect squares. Square root of 9 is 3, square root of 4 is 2. Don't forget the plus minus in front of that. And then all I have left to do now is subtract 5/2 from both sides, and I'm going to get x is equal to negative 3/2 minus 5/2 and positive 3/2 minus 5/2. So both of those will simplify. Negative 3/2 minus 5/2 is negative 8 over 2, which is negative 4. 3/2 minus 5/2 is negative 2 over 2, which simplifies to negative 1. And those are the exact same factors that we established at the beginning of the problem through just simple AC factoring. Again, this was a very simplistic example, but it was just simply set here to show you how to use completing the square. So use this as a template for any other problems where you're asked to complete the square. The next thing that we want to look at, and this is an explanation of how the quadratic formula is derived. I'm not going to go over all of that with you, but the quadratic formula is something you should have seen at some point, hopefully in Algebra 2. If you have not seen the quadratic formula, it's fine. We'll get through this without too much difficulty. But there's something very important that you do want to look at, and that's here in the middle of your screen right now. So the discriminant of the quadratic formula. The discriminant is what's underneath the radical in the quadratic. It's the b squared minus 4ac. If that value is greater than 0, then you have two unequal real solutions to the quadratic. If the discriminant is equal to 0, then you have a repeated solution. And if the discriminant is less than 0, then you have imaginary solutions to the quadratic. And we're going to talk about imaginary roots later on. So example 5 wants us to use the quadratic to find the zeros of the function. Now the quadratic formula is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And remember, the naming conventions for our quadratic or any quadratic equation is ax squared plus bx plus c. So if we use those labels that we have there and substitute it into the quadratic formula, b is negative 5, so the opposite of negative 5 is positive 5, plus or minus negative 5 quantity squared minus 4, a is 3, c is 1, all over 2 times a, which happens to be 3. So all we did was just substitute in numbers, the values from the quadratic equation that we were given. We will simplify this, so we get 5 plus or minus. That's going to be 25 minus 12 over 6. Simplify further. 25 minus 12 is 13 over 6. And the square root of 13 is irrational, and that does not reduce any further. So there are two solutions. 5, we get x is equal to 5 plus radical 13 over 6, and x is equal to 5 minus radical 13 over 6. So that's an application of the quadratic equation. You do notice right here that our discriminant is positive 13. Since that is a greater than 0, then it does indicate that we have two unequal real solutions. And we see that indicated right here by the 5 plus radical 13 over 6 and then 5 minus radical 13 over 6. For the purposes of this class, please don't use decimal approximations unless you're told to. Keep everything as an exact answer. And what we see here for this solution on example 5 are two exact solutions. For example 6, find the real zeros, if any, of the function f of x equals 3x squared minus 4x plus 2. So again, let's just label our values. And we're going to have x is equal to the opposite of b. So opposite of negative 4 is positive 4, plus or minus the square root of b squared minus 4 times a, which is 3, and c is 2. All over 2 times a. So if we simplify what is underneath the radical, we get 16 minus 24 over 6. And then we simplify a little bit further again. 16 minus 24 is negative 8 over 6. And here we see a case where the discriminant, what's underneath the radical, is negative. Now, if you recall from the note at the beginning, or just prior to example 5, if the discriminant is less than 0, then that means we have two complex zeros to the solution. So this one, since it has a negative discriminant, has no real solution. And then let's see, I think we're getting towards the end here. Just a couple more examples. Yeah, sorry for scrolling through there. Hope nobody freaked out over that. We are looking for the point of intersection of two functions. So the point of intersection of two functions is the shared values that would be a solution to both equations simultaneously. And in the case of example 7, we'll see how to do that. We're given f of x is equal to x squared plus 5x minus 3. G of x is equal to 2x plus 1. And then it just says to simply solve f of x equals g of x. So where those two equations are equal to one another is the point where they do intersect. We get x squared plus 5x minus 3 is equal to 2x plus 1. And we're just going to solve this. So let's subtract the 2x from both sides. And also let's subtract the 1. I hope that's okay if I do this all in one step. And we end up with x squared plus 3x minus 4 is equal to 0. Now we can look at this and determine whether or not this is a factorable equation. Looking at the constant term is -4. The middle term is +3. We can see that the factors of -4 that add up to 3 would be +4 and -1. So we can write this out as x plus 4, x minus 1. And when we use the zero product property, we take each factor, set it equal to 0, and then solve for x. So we get x is equal to -4, x is equal to 1. So the solution in this case is when x equals -4 and when x equals 1, those two equations are equivalent to one another. Solving equations that are in quadratic form, find the real zeros of the function x plus 2 quantity squared plus 11 times x plus 2 minus 12. I'm going to show you kind of a little trick here. What we see is I have x plus 2 and x plus 2. Now you could expand the x plus 2, you could distribute the 11, and then generate this larger quadratic that can be simplified and condensed down into a quadratic trinomial, just a quadratic with 3 terms. Or we can do this little mathematical trick. Let's start out by saying, let's let u equal x plus 2. So if u is equal to x plus 2, we can rewrite the original problem as u squared plus 11u minus 12. Because if you notice right here in the original problem, the x plus 2 quantity squared, we just said x plus 2 is u. And then I also have 11 times x plus 2, which we said x plus 2 again is u. So here we have this quadratic in terms of u rather than x. And this is one that we can factor. We know that this will factor into u plus 12 and u minus 1. And what we want to do is go back to our original variable here in just a second. So we have u plus 12 equals 0 and u minus 1 equals 0. So in this case I have u is equal to -12. And in this case I have u is equal to +1. Now that is not my solution because the original problem was in terms of x. I keep touching my face and we're not supposed to do that. So we need to go back to our original variable. So I'm going to do another substitution, except this time I'm reversing the process. So now I'm going to replace u with x plus 2 because that's what we defined it to be at the beginning. And I'll do the same thing over here. And now I can solve both of these equations for x. So I'll subtract 2 from both sides here to get x is equal to -14. I'll subtract 2 from here and I get x is equal to -1. And there are my solutions to the original quadratic expressed here that I just highlighted there for example 8. And let's see, finally with example 9, it says find the real zeros of g of x equals x plus 2 radical x minus 3. This does not appear to be quadratic. I just touched my face again. This does not appear to be quadratic. However, we can write it as a quadratic doing the same technique that we did in example 8. Here it's not as clear what we want to let u equal, but if we notice our linear term has a square root of x. So let's let u equal the square root of x. So what that means is for this first term to be x, it would have to be u squared, because the square root of x squared is going to be x. So now we have u squared plus 2u minus 3. So even though it didn't appear initially to be a quadratic form, we can express it in quadratic form, and this again is something that we can easily factor. We would get u plus 3, u minus 1, and we have our factors u plus 3 equals 0, u minus 1 equals 0. We will solve to get u is equal to negative 3 and u is equal to positive 1. Again, we're at a point where we have u is equal to square root of x, because our original variable was in terms of, our original function was in terms of x. So we need to go back to that original variable. So now we will replace u with the square root of x. And in both cases, to get x by itself, we would have to square both sides. So we get x is equal to 9 and x is equal to 1. And this will represent the two solutions for x plus 2 radical x minus 3. We can verify these two solutions by substituting them back into the original equation. One thing I do want to point out is we do have what's called an extraneous solution here, and that is indicated right here. We can never take the square root of a number and get a negative solution. So x equals 9 is not going to be one of our possible solutions to this problem. So we can check 1 to make sure that it does work, and we get 1 plus 2 times the square root of 1 minus 3. 1 plus 2 minus 3 does in fact equal 0. So 1 is a 0 of the function. If you don't believe me about 9, we can check that as well. 9 plus 2 radical 9 minus 3 is going to give us 9 plus 6 minus 3, which does not equal 0. So that's how we know, simply by the simple fact that we cannot take the square root of a number and get a negative solution. So we know that x equals 9 is extraneous. The only possible solution is going to be x is equal to 1. There will be another video probably later on in the day on Tuesday for you guys to watch. But I do just want to encourage you all to please ask questions. Feel free to check in with me anytime you want to. I will probably set up a Zoom classroom meeting for us where we can all just kind of get together one day this week and answer any questions you may have as a class, and just to kind of just check in with each other and have some sense of normalcy to what has been a very disrupted and chaotic situation. I hope everybody's doing very well, and I will be talking to you guys very soon. Have a great night.